And what are the importance of having GVF profile in civil engineering practice? The first one is it can detect any changes of fluid behavior, especially when we install hydraulic structure inside the channel. So depending on the case, the backflow profile is one of the GVF profile type, and the analysis of this situation can be solved through GVF analysis method. Secondly, in the case of dam or weir construction, it may cause inundation of fluid at several kilometers backwards. So therefore, by knowing the analysis using GVF technique, we can calculate how far the increment of fluid depth along the channel span. And thirdly, we can estimate how big of fluid area at certain location as a result of increment of fluid depth from GVF fluid type. So this course is considered the following method. There are several techniques in estimating or calculating the GVF flow profile. However, in this syllabus, in your undergrad syllabus, we are going to learn three methods, which are the direct integration method, the second one is numerical integration method, and the last one is the direct step method. In the GVF profile calculation, the changes in depth of fluid dy over dx can be calculated if we know two parameters out from these three parameters. The parameters include y1. What is y1? Y1 is the fluid depth at the beginning of the GVF profile. Yn plus 1 is the fluid depth at the end of the flow profile to be considered. And the last one is L. L is the length that is covered between these two fluid depth in the GVF profile. Okay, so let's move to the first method to calculate the GVF profile using the direct integration method. The formula for direct integration method is listed as follows. So x2 minus x1 is actually the length of the GVF profile, and in other words can be written as L or delta x. So here x2 minus x1 also can be written as delta x, or in other words it also can be written as capital L. So this formula is used when we consider between two sections or only one segment in the GVF calculation. So say we have here the diagram of the GVF profile, which is occurred when we install a weir at downstream of the channel. So this is weir, and the placement of the weir will cause the water to rise up, which is the GVF profile. So this is the GVF depth at location y1, and this is the GVF depth at location y2. So the distance between these two, this is at point x1 and this one is at point x2. So the distance between these two is delta x, or in other words it is equal to capital L, the length of the GVF profile. However, if you want to have more accurate results, we need to have more than one segment. So the more segment we consider, the accurate result we will obtain. So the segments, the more segments means we need to create table of calculation to ease our job. And the length of GVF, which is bounded by the two GVF depth, is the summation of delta x for all row of calculation. So in this case, we have more than one segment. This is segment 1, this is segment 2, segment 3, segment 4, and segment 5. So the more segment we create, the more accurate result we will get for the length of the GVF profile. Okay, let us look at the rest parameters in the formula. We have the constant parameters inside this formula. There are Y0, S0 and YC. So here inside the formula we've got S0, Y0, S0 and also YC. This is the only one calculation to be replaced inside this equation. And the rest of the parameters either we can obtain through their own formula by using standard appendix table or by using standard design chart. For instance, U here is the parameter which can be calculated using this formula. U is equal to y divided by Y0. So Y0 is the normal depth, Y is the GVF depth at the particular segment. Again, J parameter here can be computed using this formula. So J is equal to capital N divided by N minus M plus 1. So where can we obtain this hydraulic component of N and M parameters? It can be read from the standard design chart as shown in this diagram. For M parameter, we need to have the ratio of depth of flow Y with the width B. So if the shape of the channel is rectangular or trapezoidal, so here we use this ratio if the shape of the channel is rectangular or trapezoidal, so we use this ratio. Meanwhile, we divide Y with D if our channel shape is in circular shape. So D here means the diameter of the circular shape. So this ratio we use for circular shape. It's a matter of fact of changing B to D if the shape of the channel is changed from rectangular or trapezoidal to circular. So this is important because the depth of flow used for this ratio, we use the normal depth Y0 for determination of M value. Y0 here, Y0, we use Y0 here for determination of M value. And the second information is to know the channel shape. Either it is rectangular, trapezoidal or circular. Here is rectangular, it is missing down the description for this line. So this is referred to the rectangular shape. So rectangular shape, our Z is equal to 0. So this all is referred to trapezoidal shape, depending on the side slope of the channel. So the trapezoidal shape is ranging from 0.5 up to 3. And the last line here is referred to the circular shape. So we need to intersect the two information here from the y-axis with the line in the middle of the graph to obtain the M value on the x-axis here. For example, if we want to calculate the ratio of Y0 over B or D is equal to 0.5 when we divide these two parameters, either this one or this one, the answer is 0.5. So what is the value for M, especially if we consider our shape is rectangular or change to trapezoidal or circular? So looking at this design chart, the ratio of 0.5 is here. So let me erase this first. So 0.5 is located at here. So 0.5 is here, the ratio, and then we need to cross or draw the temporary line to intersect at the respective channel graph. So we have 3 cases here. The first one is to know what is the value for m if the ratio of y naught over b is equal to 0.5 for rectangular. So we need to draw a temporary line which is intersects with this rectangular shape. This is rectangular shape. So when we cross, we found that the answer is equal to 3. So our m is 3 for rectangular. How about trapezoidal? If trapezoidal, here we assume that their side slope is 0.5. So we need to extend the temporary line here until it intersects with the respective trapezoidal shape line as z equal to 0.5, and then we read the m value at the x-axis here. So it is approximately equal to 3.3. So this 3.3 is the m value for trapezoidal shape. And the last one, if we extend until it touch the circular line here. Okay, here is the intersection of between 2 points. So we project the line until we can read their values on x-axis. So their value is equal to approximately 3.8. So this 3.8 is m value for circular shape. Right. Some of you might ask, what if our shape is the other shape, which is triangular? So for triangular shape, not to worry, because we don't need to use this design here. Their values is taken by default as 5 in all cases, regardless of their side slope as shown in this table. So in this table, just take the values and just replace in the J formula. So for m, by default, their values is 5, and n for default, their values is 5.33, and these two should be substituted in this formula to obtain J value. So the n value from the design chart also apply the same procedure. This one also apply the same procedure. However, here on the y-axis information, so looking at this diagram for m hydraulic exponent, so n here we need the ratio of y over b as well and y over d, but here y is changing from y naught from previous determination of m exponent, hydraulic exponent. Now at n determination we use yc, the critical depth. So please be careful, and remember, I repeat, for n value y here on y-axis we should use y naught, and for n value determination y here we should use yc value. For example, for n value using this design chart, say that the ratio on y-axis yc over b or yc over d is equal to 0.4, and we need to draw a temporary line to cross the respective graph line for rectangular, for example, trapezoidal say at 0.5 and or circular. So we draw here temporary line crossing the respective line for each different shape of the channel. So the first one, say we want to find what is the M value for rectangular shape. So we've got here the intersection point here, the first one, and extend to the another shape, which is trapezoidal at side slope of 0.5. So we have the second intersection, and the last one is the intersection for circular shape. So we've got here their points. So the intersection of their point here, we need to project it to x-axis to obtain what is the n value for this ratio. So after we locate their intersection depending on the shape we consider, for rectangular the answer is approximately 2.75. So here is 2.75 for the shape, rectangular shape, at ratio YC over B equal to 0.4. For trapezoidal is approximately 3.25 if we project this line to the x-axis. So we will get the answer is equal to approximately 3.25 for trapezoidal, whereas for circular shape is 3.6. So here we draw a temporary line to read the n value on x-axis 3.6. This is for circular shape. And how about V shape? If we have triangular shape here, again we need to refer to this table. So just take the default value, which is 5.33, to substitute into the J equation. So these are two values, the default value for M and N. You need to remember because we won't provide this value in your final exam. So this value you need to remember. And one more thing is the very wide channel shape. The very wide channel shape, you also need to memorize M equal to 3 and N equal to 10 over 3. So here if you are given another description saying that your channel is very wide channel, so by default their values for M and N, M should be taken as 3, whereas N should be taken as 10 over 3. So these two also you need to remember for your exam. Sorry. So again, no need to use design chart for them in the case of very wide channel. So very wide channel, no need to refer to any design chart. So straight away use these two values to substitute into the J equation. So the rest of the shape you must refer to the standard design chart. Okay, so we have finished with N and M values here. So I jot it here once again. Okay, for M value here, we take their values from the GVF chart. So what should we be very careful here at y-axis? Y-axis we need to use y over b depending on the shape, if rectangular or trapezoidal, and y over d. So here y here we need to use y naught, the normal depth. Y here equal to y naught. So if we have a very wide channel, so if the channel is very wide, So use straight away M equal to by default 3. So no need to refer to any design chart. No need to refer chart. Okay, settle with M, and then to conclude for N, and here again we need to use N is read from the GVF chart, another GVF chart. However, here and here, if you refer to y-axis, we have the ratio between y over b or y over d. Both y here, we should use y equal to yc, the critical depth. So very wide channel, if very wide channel, if very wide channel, so we need to use n equal to 10 over 3. So the remaining parameters from this equation is the value of function un and also the function for vj. So here we have fun, fun, fvj, fvj. So how can we obtain their values? It is from the appendix table. Okay, let me explain how to use this table. So we need to refer to this table. So first, values listed horizontally here on the first row here, yeah, is referred to n or j function. Instead written as n, here the values here is also used for j parameters, n or j. So all these values is referred to n or j parameters. So at above here. And also we have the left side here is referred to u or v function. So here only written as u. Also we can use this value for v parameters. So v or u should be used this value at the left side of this table. And together we can combine the reference values from the top row and the left column here. Then we will get the values for function fun and fvj. So in the middle value here is actually the answer for function all here located in the middle of this table is the answer for function fun or fvj. So I give the example of the first scenario. So say that u or v value calculated from their formula is 0.3. And n or j values calculated from their formula is 2.6. So let me erase this first. So 0.3 for v or u parameters is located here, 0.3 here, and say that the n or j parameters calculated from their formula, we found that their values is 2.6 here. So what is the function of un or function vj from this table? So we need to cross this. So here we need to cross it with each other. So when we cross this, we will find that the cross line will intersect at this number. So the answer for fun or fvj for this first case, the answer is equal to 0.304. This is the first case when we have the direct intersect between the vertical values from the n or j values with the horizontal values from V or U parameters. And the second scenario is when we have either one of the function U or V or N or J in the middle of this listed value. It is somewhere in the middle between these two or these two. So therefore in this case we need to perform interpolation to obtain the answer. For instance, say that the function of un of Vj is 0.25 and 2.4. So let's say the function that we interested to find is at this value. So function u equal to 0.5, 0.25, and the n function here is equal to 2.4. So we locate the u here. We need to find the closest number in at the left side of this table. So u here is located between 0.24 and 0.26, whereas for n parameters here is read from this column, so we need to intersect this with this. So 2.5 is located in the middle of 0.24 and 0.26. So because it is in the middle, therefore we need to perform interpolation here. Here you need to do a simple calculation like this. The first step is to draw this diagram. So you need to draw this diagram, a simple trapezoid diagram, which has the bigger shape, and also this is the bigger shape, and also the smaller shape. And at the top here we label them as our function answer. So here at the top here is actually to find the answer for function un or function vj. This is no answer at the top of this shape, and at the bottom here is the value for u or v. And now we insert the values on this diagram. So here we have the values taken, which is in the middle is 0.5. This is the value that we are interested to find. What is the answer for function, their function? So 0.5 we don't have any value, so we put here as the unknown x. So at the left is the lower value, whereas at the right side here is the higher value. So 0.24 here we put for u here 0.24, and here 0.26. What is the respective n values at 0.24 and 0.26 taken from here, from this table? For 0.242, the function for this is 0.242, and for higher value their function is 0.263. So now we do the calculation. So this is for function at n or j, which is equal to 2.4. So the calculation should be like this. So 0.263 minus 0.242 divided by 0.26 minus 0.24. This is the bigger trapezoid, and then we take the ratio, the similar technique for the smaller trapezoid here. So to write it down here, to jot it down here, 0.263 minus 0.262 divided by 0.26 minus 0.24 is equal to x minus this smaller trapezoid. So x minus 0.242 divided by 0.26 minus 0.24, and finally when we arrange this, bring to left and right, and finally we obtain the S answer, which is representing the F and N values at U equal to 0.25. So this is our S answer in the middle here, which is represented by the X values here. Okay, next we have the third scenario here, when both function of U or V or N or J lies in between of these listed values. So say that the function is somewhere in the middle these two, and also in the middle these two. For example, say that the function of UN or VJ is function 0.25 for U and 2.5 for N. So the function here, we are interested to find, let's say we have 0.25 for U and 2.5 for N. So 0.25 is located in between 0.242 and also 0.263. So here 0. Here the first one 0.25 is located in between these two values at the first lower values for N. This 2.5, this lower value, and this upper value. So the first step is it is located somewhere in the middle here. So we need to draw first trapezium like this and label their values. So draw the trapezium. So draw the trapezium, which is representing our answer at N or J, which is equal to at 2.4. So here is the value that we are interested to find at 0.25. Here 0.25, and the lower value is 0.24, the upper value is 0.26, and what is their function answer here? 0.26. we take the biggest value, which is 0.263, we label it here, and the lowest value is 0.242, and this is the first X answer, which is representing 0.25 at N or J equal to 2.4. So solve this using the same technique, so therefore we will get X1 equal to the first answer. So this is the point, the first interpolation that we made at N equal to 2.4. So we will get our answer here. So next we need to perform the other trapezoid at N or J, which is at the upper value, and here at 2.6. So the same technique applies. So we need to draw another trapezium, which is representing at N or J equal to 2.6. So here we have 0.24 here, the lower value at U or V parameters is the function for U N, say, and this one is 0.26, and this is 0.25. We are about to find the another intersection at 2.6 n parameters. So this is x2, this is x1, this is x2, somewhere in the middle here, x2. So this value we take the largest one 0.262 and the lowest one is 0.242. So do the same calculation to obtain what is x2 equal to this answer. So now we've got these two answers which is in between, but now we want to focus the accurate answer at the exact value of 2.5 here. So therefore we need to perform the last interpolation, the third one, which is representing the S1 and S2 to get what is x3. So x3 is located here, just on the line which is representing the values for n at 2.5. So this is the point for x3, which is in the middle between 2.4 and 2.6, and also between 0.24 and 0.26. So this is our final answer. So this is the last one. So here is x1, the lower value s1. This one is s2. This one is s2, and then we want to find what is s3 here. The final answer that conclude our function at 0.25, 2.5. So s1 here is at 2.4, at 2.4 here, and this one is s2, their values here is at 2.6. So the s3 value here is at n value at 2.5. So this s1 has been calculated before, s2 has been calculated before. So therefore we've got all the values inside this diagram. Therefore we can find what is x3 values. Okay, so there you have it. To conclude with values of function un and vj here, either un or vj, we covers a wide range of n or j. It will be started from 2.2 here until the table extends to 9.8. Yeah, until 9.8. Until 9.8 here, and also it will cover from, for u of v here, start from 0 until it cover to 20. So the function has quite a big number for the answer for function fun or fuj. Okay, the subscript of 2 and 1 here are referred to, and 1 here are referred as the value of the current row S2 and previous row S1. So this is the current values. If we are creating the table of calculation, this 2 is referring to the current value on the row, and 1 here is the previous value, which is at the birth of the current values. This is the case if we calculate more than one segment, like this picture. So like this picture, so here we have y1, and this will be y2. So this is will be y2, and then when we want to move to the next segment, the second segment will be y1 new, and this one will be y2 new. And when we move to the other segment, which is the third segment, so this one will be y1 another new, and this one will be y2 new. So it will be repeated until the last segment of this GVF profile. So in this case, we need to create table of calculation to ease our calculation.